Now let's look at an example. So here we have the graph Laplacian L, which is the discrete Laplace operator that we talked about. So the divergence of the gradients, which is this, right? So this here we denote this by L. And remember, this is the product of two matrices. So here, it's actually very easy to read from a graph. So when given a graph, you don't have to always list off what is the incidence matrix or the divergence, the gradients, and then to multiply these, you can actually read it from the graph. So let's see how we can do that. So when you're given a graph with nodes and edges, so sometimes you might also have weights on these edges. So for example, this is our graph with 6 different nodes. So here L, the discrete Laplace operator, is always going to be in the dimension of V cross V. So the number of nodes by number of nodes here. So we'll have a 6 by 6 matrix here. And the way you're going to assemble this up is that the diagonal, meaning this line here, is going to be the degree of the node. So if you look at each one of the nodes, right, for the first one, for example, the degree here is a weighted degree. So every incidence as that's sticking out from this node. So you have a edge that's edge that's weight 1 and the other edge weight for 2. So add these up and you get this 3. And similarly, you go ahead and add up all of the weights of the edges that's going out from 2. So here you get 5. So all of these ones, you get the diagonals like this. And then for this graph, because it's not directed, so meaning that there's no edge directions. So what you will see here is that this L is a symmetrical matrix, right? So for the previous one, when we have the different orientations of the edges, then you will have different weights. But in here, for example, we have a undirected graph. So here the matrix here is symmetrical. So here, how did you fill this up? Is basically you take 1 and take a look at what is the direct neighbor of this node. So you have 2 and 5. So for 2, there is an edge of 2 that's connecting 1 and 2. So here, this is matrix L of first row, second column. So 1, 2, this means the direction between 1 and 2, and this is negative of its weight, right? So it's negative 2. And then there's another weight, there's another edge connecting 1 and 5. So this is L15, right? So first row, fifth column, and this is negative 1, negative of its weight. And you do the same for the second node. So the second node is connecting 1, and it's so you're going to put a negative 2 here, and you put a negative 1 because there is a edge that's connecting 2 and 3. And also you have a edge that's going from 2 to 5, so that's a negative 2. So you go ahead and do all of this. So one way of doing this is that you do analysis for each node. What is the connecting neighbors, or you can just fill up the upper triangle and then just map it, right? So because it's a symmetric matrix, so you may just fill up the top half and then you get the lower half for free, okay? So either way, this L graph Laplacian is very easy to get from either graph, from any graph. When you're given a graph, whether it's directed, whether it's weighted, you can just get this out. You don't have to always do the gradient and the divergence and to multiply it, okay? So this is, sometimes we just kind of skipped the part where you have the divergence of the gradients and directly talk about the graph Laplacian. So just think about this as you directly take the second order derivative on it. First, it's its edges, and then it's first its nodes and then its edges. And something that's very interesting that's corresponding to the graph Laplacian is its quadratic form. So if I multiply L by a vector x, so the x is in the dimension of v, right? So you have v elements in this vector, and then you multiply x transpose times L and x. So think about what is the dimension of this. So x, if x is a vector, so x transpose is going to be 1 by v, right? 1 by the size of v. And L is a v by v. So I'm going to write it here, v by v. And then the last one is v by 1. So you're going to get a scalar out, right? So in the end, you should get a scalar. So this kind of tells you what is the basically like the differences between each node. So in the end, you see that there is a xi minus xj squared. Basically, it's measuring the difference, the square of the difference, and also distributed by its weight. So this tells you that how smooth, basically how different is this graph. So for each node, if the node has a value, what is the difference between the value? And you can think about, if the values are all equal, right? For example, 1 and 2 has the same value on its node, then this will be 0. So the minimum of this is 0. But then because the nodes may have different values, so this is always going to be bigger or equal to 0. So this is what sometimes we measure maybe like energy flow of this network from one node to another. If we have a different values on these two, then like you can find out what is the way to make the whole system energy efficient by assigning the different values on the nodes to make sure that the difference, square of the difference is minimized. Okay, so so this page is basically telling you we can write the discrete Laplace operator as a matrix, and that matrix is very easy to read from any graph. And also we introduced this quadratic form, basically measures the energy of all of the nodes value. So if we wanted to evenly distribute, we wanted to distribute the values in a energy efficient way, how is the way to make sure that the sum of the difference squared is minimized?